All right, let's look at some examples of relations. Let's carefully try to understand this relation that's described here. First, I have to consider the set A that the relation is defined on. It is supposed to be the set of all strings of zeros, ones, and twos of length 4. So they've given us some example in the question itself, but I can just build some other ones. So here's a string of length 4 that has all zeros. Here's one that has all zeros and a 1, and so on. I'm just listing a few of these things. If you're familiar with base 3 counting, you can sort of construct all strings of this form by counting up in some systematic manner. Okay, so A is this finite set. I'm going to ask about its cardinality just as sort of a follow-up and a preview for the counting section, which we'll get to later. But what I understand is these are the elements that I'm dealing with, and the relation that's defined is going to be a collection of ordered pairs of these elements. So R is defined in the following way. Take two strings, S and T, and we're going to say that S is related to T, or, formally this means that the ordered pair S comma T is in R, but that's always awkward to write. We usually just write SRT. And that's going to be defined to mean that the sum of the characters in S is equal to the sum of the characters in T. So you take all the numbers that appear in the string S and you add them together and see if that's the same when adding the characters in T. So let's kind of crank out A, B, C, and D. These are easy yes-no questions. You may as well pause the video and see if you end up getting the same answers as me. To check if 0, 1, 2, 1 is related to 2, 2, 0, 0, I add the characters in the first string and I get 4, and I add the characters in the second string and I get 4, so the answer is yes. Okay, B, I add and get 3, I add and get 4, no. I add and get 7, and I add and get 6, so that's a no. And then finally, I add and get 5, and I add and get 5. That's a yes. Okay, so I've got some sense of, how this relation works. Some ordered pairs end up in the relationship, in the relation, some don't. But I'm going to ask some maybe harder questions that preview some concepts to come in the course. What is the cardinality of the set A? How many strings are there of zeros and ones? Pause and see if you can sort that out. Okay, so we'll see this in more detail later in the counting section, but you can sort of, perform this counting by going through a sequence of steps to construct an arbitrary length 4 sequence of 0, 1s, and 2s. So you sort of think of it this way. Your string can either start with a 0, a 1, or a 2, and the second character in the string is also a 0, 1, or a 2, and this is, listing out all the possibilities for the 4 characters in your string. Well, the idea is that if, so I've observed here that I have 3 choices for how the character can start, and for each one of those choices, you're going to have 3 possibilities for what the second character is. So you're going to have like 0, 0, 0, 1, 0, 2. You can have 1, 0, 1, 1, 1, 2. And you can have 2, 0, 2, 1, 2, 2. That was 9 ways to start a string of length 4. And then I can sort of just continue the logic. Given any one of those 9 starting possibilities for the first 2 characters, I'm going to have 3 options for what the third character can be, and then the last character, again, I'm going to have 3 options. So the cardinality of the set A ends up being 3 to the 4th, which is 81. Again, we'll see more of this later, but as long as we're dealing with this set, it feels like a natural thing to ask. Second question, what about this set right here? Pause and see if you can just understand what the set says and then figure out the cardinality. Well, this collection of elements of A are all of the strings in A such that that string is related to the 0000 string. So what would this take? How would S be related to 0000? Well, it would have to have the same sum as the sum that 0000 has. Well, that's 0, and there's only one member of A that has that sum. So there's exactly one element, exactly one S that satisfies this condition, that is the 0000 string. So my answer to this question, the cardinality of this set, is 1. Let's do the same thing for a different string. So how many strings are related to 0100? How many strings have a sum of 1? Well, 100 does, 0100 does, 001, and finally 0001. These 4 strings that I see right here all are related to 0100. Just note that 0100 is related to itself. I mean, it has the same sum that itself has. So the answer to this one would be 4. Okay, what do we have next? Number 3. This is sort of like a general question about this relation. If you know that S is related to T, do you know that T is related to S? And this is just sort of a consequence of how the relation is defined. The answer is yes, because just read the English. The sum of the characters in S is equal to the sum of the characters in T. That means that the sum of the characters in T is equal to the sum of the characters in S. It's just how equality works. The answer to this is yes. What about this? Oh, well, first let me say, we're going to call this later symmetry. So we're going to say that this relation, since it satisfies this conditional, we're going to say that R has symmetry. All right, now this next one. If you knew that a string S was related to a string T, and furthermore that that string T was related to a third string R, could you conclude that S was related to R? Again, the answer is yes if you just read the definition of R carefully. If the characters of S sum to the same that the characters of T do, and the sum of the characters of T is the same as the sum of the characters in R, then you can conclude that the sum of the characters in S is equal to the sum of the characters in R. So we're going to say later that this means that the relation has transitivity, or that R is transitive. Okay, moving on to the next example, we're just getting a feel for dealing with different types of relations on familiar sets. Here, I've got the real number system. I typically draw it like that. And we're defining 2 different relations on the same set. And since relations on the set R would be subsets of R cross R, it's sometimes convenient to graph, because R cross R is a familiar space. It's the Cartesian plane, and we like to just draw objects in there. So let's see here. R is supposed to be the collection of ordered pairs such that x squared plus y squared is 4. You could also write this out. I mean, this is written out in the formal set notation. You could also say it like this. You could say x is related to y means that x squared plus y squared equals 4. Okay, so they're actually asking us to graph that relation. Let's graph R. Well, the collection of ordered pairs that satisfies that equation is exactly a circle. Hopefully you recognize that formula of radius 2 centered at the origin. So there's a graph of the relation R. And now S is, similar. It's a collection of ordered pairs from R cross R. But here the defining formula is that x equals y. So I want to graph all of the ordered pairs of real numbers where the first coordinate is equal to the second coordinate. So you know that, let's use a different color. You know that to be a line like this, x equals y. And once you have these 2 relations graphed, so I did part 1 and part 2, I can graph the union and the intersection, kind of thinking of this as some sort of strange Venn diagram or something. So let me get a new coordinate plane here, and I'll graph the union and the intersection. So for the union, R union S, I take everything in S and I add to it everything in R. So I just get this picture that is all of the ordered pairs that are on the circle or on the line. So joining these two sets together to make one is the set R union S. For the intersection, I'm trying to graph all of the ordered pairs that lie both on the circle and the line. So that's just 2 points, square root of 2, square root of 2, and negative square root of 2, negative square root of 2. So this is our intersect S because it is the collection of all ordered pairs that simultaneously satisfy this equation and satisfy that equation. And then just physically, they're the intersection of the green set and the black set up there. Here's a good question, a little follow-up question to think about. What are R inverse and S inverse? So pause and think about that. Formally, R inverse is all of the y comma x's such that x comma y is in R. But here's the thing. If x comma y is in R, that means that x squared plus y squared is 4. But that also means that y squared plus x squared will be equal to 4. So if xy is in R, you automatically know that yx is in R, and there are no other types of elements in R. R is the collection of all ordered pairs that satisfies this equation, but if you flip the role of y and x, you see that's exactly the same thing as gathering together all of the yx's that satisfy that equation. So going through that argument, I see that R inverse is actually equal to R. And actually, the exact same thing can be said about S. If you're gathering together all the xy's where x equals y, that is literally the same thing as gathering together the yx's such that x equals to y. So R and S happen to be their own inverse relations.